For storage, we have our JBOD and JBOF sleds, and this is just a bunch of disks or flash, and all of these are direct attached to compute nodes. And for applications that require a lot of RAM, we have two processor systems, each with 256 gigs of RAM and a 25 gig NIC. So when we think about running our services in the data center, we have each major component, compute, storage, and RAM, running on a very wide network. Depending on which service is being built, engineers will allocate some number of each. All of these server designs are shared via the Open Compute project. Now, our company was founded on open source software. We began with our LAMP stack, with the standard LAMP stack, and then we started building our own services as our needs diverged from what was readily available. When it came to building custom hardware in data centers, we stuck to the open source model and launching the Open Compute project in 2011. For all of our core infrastructure, we've worked with the community via OCP. There, we, Facebook, and the large OCP community focus on designing open interfaces, sharing hardware implementations. In 2016, we also founded, with a number of telecom partners, an organization focused on improving the tech between data centers and the edge, and this is the Telecom Infrastructure Project. Now, both TIP and OCP focus on models of open collaboration and open interfaces. Now, at Facebook, we're responsible for building and growing large infrastructure to support 4 enormous communities using our main apps. And those communities drive a ton of traffic. Billions of messages sent per day, millions of live broadcasts, and more recently, significant increases in machine learning workloads. We're building to meet the demand of growing apps, as well as a serious uptick of internet growth across Asia. Our data center footprint spans 15 locations, 3 continents, with our newest data center announcement in Singapore. Now, if we get back to the data center and take a closer look, when our engineers are designing a service, or really any kind of application, the work is always in trading off 4 basic components: compute, storage, memory, and network. Now, compute is still growing. Moore's law is not dead, well, I guess Patterson just said it was dead, so it's slowing, right? And it's much slower, it's growing much slower than the previous 10 years, but we still see plenty of growth ahead. Storage is mixed. Hard drives face challenges in delivering increased IOPS per terabyte, while flash, having recently delivered fantastic improvements lately going to 3D, faces a future where densification is going to be trading off against endurance, write endurance, and it's going to present durability challenges. RAM continues much as it has over the last several years. Network, however, has been incredible. The improvements in optical continue to deliver 4x the bandwidth for only 2x the power. This resource, more than any other, is the one that we've chosen to build large at Facebook, while trading off more network demand for less consumption elsewhere. As our infrastructure grows, we see one workload that demands a new component, and this is machine learning. So neural networks will require new hardware accelerators to meet the computational demands that are quite different from normal CPU workloads. Now, every time I think about building a machine learning accelerator, I think of all the math that needs to be done. It reminds me of a device from 1980. This is the 8087. Okay, who remembers this? Seriously? Come on. All right, what did it do? Floating point math. All right, so the 8087 from 1980 did floating point math. It was tremendously expensive and ran alongside the 8086 processor to increase floating point math capacity. This whole talk is about hardware repeating itself. Except this time, rather than needing more floating point math, we need more integer math. Multiply accumulates to be specific, and what we need is custom hardware to multiply matrices together. It's really all it is. And so given our history, it shouldn't be much of a challenge, or it shouldn't be much of a surprise that when it comes to machine learning, we do it all in the open. So at Facebook, we've invested heavily in the software side. We've contributed to open source and worked with other leaders in the field on interoperability projects like Onyx, as well as PyTorch and Caffe2. All of these now come under the banner of PyTorch 1.0, which will have its first developer summit next month. PyTorch includes projects across vision, language, reasoning, and tools. But today, I'd like to talk about one project in particular, which is GLOW. Now, when you compare the throughput of running machine learning workloads, specifically inference, on traditional CPUs, compared to running it on a hardware accelerator, the speed up on the hardware accelerator is between 10 and 30x on either a TCO or watts basis. Inference is the act of looking up an answer or recognizing an answer in machine learning. It's just the forward part, and that part is usually pretty time constrained and resource constrained. Our compiler, GLOW, is for machine learning workloads. It takes a high-level AI graph and renders it to bytecode for hardware accelerators. Now, returning to the data center, the hardware accelerator is an inference accelerator. It's the new math coprocessor for neural networks. Now, it will be a new component to use in data centers for heavy machine learning workloads. And if we zoom in on the design of this inference accelerator, we see that, much like how we think of a data center, there will be decisions to be made around the sizing of compute, memory, and buffers. And critically, there's a new resource in these chips, which is designed for general matrix multiplication, or GEMS. The layout of these chips determines the network between the resources, or bandwidth between the resources, available to each of these components. Now, the hard part, though, is that these ratios are fixed when the chip is designed. And so each ASIC that the industry produces is going to bet on a combination of these resources being valuable in the marketplace. Now, this is hard work. Each bet will be realized 2 years after it's made. So winning in this space will be a combination of insight, execution, and luck as workloads move around. So why did we create GLOW? We recognized that new tools were needed for hardware acceleration. We also wanted an open ecosystem as well as interoperability. And at Facebook, we were thinking, like, how could we best contribute to machine learning? And we were lucky enough to have a number of great compiler people who'd worked hard on HHVM, which is our JIT compiler for PHP, as well as other projects at Facebook. So lending a hand in this way came pretty naturally. So we created this compiler GLOW to translate high-level graph descriptions to machine code, targeting several inference processors and machine learning environments. This is the history that Dr. Patterson told, but in reverse. We know the fragmentation is coming because nobody knows exactly which set of combination of resources is going to win. But we want to allow machine learning developers to really just focus on the machine learning part, creating that graph, and not have to worry about hand coding hand coding for each hardware platform. So the whole idea is you take the high-level graph and then you let GLOW translate it to the machine learning target. Now, We're very happy to announce that 5 companies have committed to working with Glow and supporting this software ecosystem. Marvell, Intel, Esperanto, Qualcomm, and Cadence. They've all contributed significantly to shaping Glow, and we're all very lucky to work with them. Our approach to semiconductors is to build a strong team internally and then really collaborate with industry leaders and innovators like these. We've always favored a community-based approach over going it alone. So, when building infrastructure, both hardware and applications are needed. These companies are all coming out with great silicon over the next year or two, but the community isn't complete without all of you. So I'd like to invite all of you to work with PyTorch and Glow and contribute to the code base so we can all drive this hardware acceleration for machine learning to develop much, much faster. So I'd like to thank the LLVM community, which powers the traditional CPU target in Glow, as well as several of our data structures within Glow. And we hope to see a number of you at the PyTorch 1.0 Developer Conference next month. Thanks for your time.